To understand special relativity, we need to travel back to the 19th century. At that time, science had two remarkably successful models for describing the world. One was Newtonian mechanics, which explained the motion of objects. The other was Maxwell's theory of electromagnetism, which described electromagnetic phenomena, including the behavior of light. The problem was that these two theories did not fit together. Rather than diving too deeply into the technical details, let's explore this contradiction through a simple thought experiment. Imagine two spacecraft in motion. One is moving away from Earth at a speed of 5,000 kilometers per hour, while the other is approaching Earth at the same speed. To an observer aboard the departing spacecraft, the approaching ship is moving at 10,000 kilometers per hour. This is perfectly reasonable. Speed is always measured relative to something, whether it is the Earth, the Sun, or another object. In this case, the relative speed between the two spacecraft is therefore 10,000 kilometers per hour. Now imagine that someone throws an object from one spacecraft to the other at a speed of 100 kilometers per hour. To the crew of the other spacecraft, that object will arrive with a relative speed of 10,100 kilometers per hour. So far, everything fits perfectly with our everyday intuition. The situation takes a strange turn, however, if we replace the thrown object with a beam of light. According to both experimental evidence and theoretical models, light does not arrive with its speed plus the spacecraft's additional 10,000 kilometers per hour. Instead, it always propagates at the same constant speed, the speed of light. It does not matter how fast the spacecraft are moving or in which direction. Light simply refuses to adapt to anyone. This unusual behavior arises from a deep contradiction between Newtonian physics and Maxwell's theory of electromagnetism. Einstein's revolutionary insight was that instead of trying to explain this result, he simply accepted it as an axiom. What if the speed of light is the same for every observer, regardless of how fast they are moving? At the same time, all observations suggested that motion can only be defined relative to other objects, and that no experiment can determine who is really at rest. Let us take these ideas as our starting point and adjust Newton's laws accordingly. To do so, however, we must rethink the nature of time itself. In rapidly moving systems, time must pass more slowly. We define speed as the distance an object travels during a given amount of time. We also know that when we move towards something, our own speed must be added to its speed to obtain the relative velocity. The same should be true for light. Yet experiments showed otherwise. If time slows down aboard a moving spacecraft, however, this slowdown precisely compensates for the effect of motion, ensuring that the speed of light remains the same for all observers. It is possible to calculate exactly how much time must slow down, an effect known as time dilation, to make everything fit together. But slowing down time alone is not enough. To preserve other fundamental physical principles, such as the conservation of energy and momentum, additional corrections are required. One of these corrections is length contraction. Objects moving at high speeds become slightly shorter in the direction of motion. This effect is negligible at everyday speeds, but becomes significant as an object approaches the speed of light. Another important effect is that rapidly moving objects become increasingly difficult to accelerate. The faster an object moves, the more energy is required to increase its speed further. Early physicists often describe this by saying that its mass increases with velocity. Together with time dilation, these effects ensure that the laws of physics remain consistent and that no material object can ever be accelerated to the speed of light. Einstein's true genius lay in reversing the usual logic. Rather than treating space and time as unchanging foundations, he treated the speed of light as the constant and allowed everything else to adapt to it. This way of thinking made it possible for earlier theories to coexist within a broader and more comprehensive framework. The most remarkable part is that Einstein's radical idea works. In fact, it describes reality with extraordinary precision. Particle physics experiments have confirmed these effects again and again. Fast-moving particles decay more slowly, exactly as the theory predicts. Today, relativistic corrections are an everyday part of modern particle physics. Without them, technologies such as GPS would not function properly. Few people realize that before Einstein's solution, there was already another theory capable of explaining the constancy of the speed of light. In the late 19th century, most physicists believed that light propagated as a wave and therefore required a medium, just as sound requires air and water waves require water. This hypothetical medium, thought to fill all of space, was called the luminiferous ether. The ether could not be observed directly, but many scientists believed that light and electromagnetic phenomena propagated through this invisible substance. Before Einstein published Special Relativity, Hendrik Lorentz and George Francis Fitzgerald had already attempted to explain why the Earth's motion relative to this hypothetical ether could not be detected. They did not begin with the assumption that the speed of light is the same for all observers. Instead, they proposed that the electromagnetic forces holding matter together somehow interact with the ether. According to Lorentz, when an object moves relative to the ether, the forces binding its atoms together change slightly. As a result, the object contracts in the direction of motion. This contraction is extremely small, but just large enough to conceal the effects of motion through the ether. The mathematical description of this phenomenon is known as Lorentz contraction, and it leads to exactly the same formula that Einstein later derived from an entirely different starting point. The difference between the two theories was not in their observable predictions. Both produced the same experimental results, the same length contractions and time dilation effects, and the same mathematical relationships. The real difference lay in how these phenomena were interpreted. According to Lorentz, there existed an absolute background, the ether, and relativistic effects occurred because moving matter interacted with this medium. Einstein, on the other hand, discarded the ether altogether and simply treated the constancy of the speed of light as a fundamental law of nature. For most people, the concept of space is still tied to Newton's idea of an absolute, unchanging stage. We tend to think of it as something that exists independently of whatever happens to be inside it. If two objects are 1 meter apart, we naturally assume that they are 1 meter apart for every observer. Common sense seems to tell us so. According to modern physics, however, this picture does not reflect reality. Back when the meter was defined by a platinum bar stored in Paris, distances were considered rigid and universal. Lorentz proposed an intriguing possibility. What if the measuring rod itself shrinks while it is moving? And what if every measuring device contracts by exactly the same proportion? In that case, we would still measure the same distances, even though what we perceive as 1 meter would actually be shorter. From Einstein's perspective, the same phenomenon can be described in a different way. Instead of saying, all measuring rods have contracted, we say that length itself is not an absolute quantity. Two observers moving at different speeds can measure different values for the same distance, and neither of them is wrong. This leads us to a much deeper realization. The classical concept of absolute space no longer has any physical meaning. Physics deals with what can be measured. If different observers measure different lengths, then it makes no sense to speak of a single absolute distance that is the same for everyone. If the speed of light were much lower and relativistic effects were obvious in everyday life, we might never have developed the concept of absolute space in the first place. If a passing car visibly compressed in the direction of motion, we would consider it perfectly natural. In such an alternative world, the idea of an absolute, unchanging space might never have arisen at all. Newton's absolute space, therefore, gave way to something far more useful: measurable, relative space. The situation becomes even stranger when it comes to time. How is it possible that an astronaut traveling aboard a spacecraft moving close to the speed of light ages more slowly than their twin who remains on Earth? Here, too, we must distinguish between two concepts: Newton's absolute time and physical time, the time measured by clocks. And by clock, we do not mean only ticking mechanical devices. Any regular process can serve as a clock: the swing of a pendulum, the vibration of an atom, the decay of a radioactive particle, or even the aging of a human being. Aging itself is an extraordinarily complex sequence of physical and chemical processes. If every process that can measure time proceeds more slowly in a rapidly moving system, then aging must also occur more slowly. It is not just the clock that runs slower. Every process the clock is intended to measure runs slower as well. This is why the issue is not that the clock is somehow measuring incorrectly, but that the passage of time itself unfolds differently for different observers. Everything we know about time comes from physical processes, and all of those processes are affected by motion. If absolute time cannot be observed or measured, then for physics it does not really exist. Just like space, the concept of absolute time loses its physical significance. What truly exists in physics is not a universal cosmic clock, but the time-measuring processes that we can observe in nature. The concept of mass also requires a similar rethinking. We are used to thinking of mass as the amount of matter contained in an object. In physics, however, mass is better understood as a measure of how difficult it is to change an object's motion. In other words, it describes the object's inertia. If we push a heavy object and a light object with the same force, the lighter one will accelerate more. According to Newton's laws, mass tells us how much force is required to produce a given acceleration. We exert forces through physical interactions. Modern physics recognizes four fundamental interactions: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. In everyday life, almost every force we experience directly is ultimately electromagnetic in origin. When we push an object, the atoms in our body are interacting electromagnetically with the atoms of that object. Now imagine a particle accelerator, where particles are accelerated by electromagnetic fields. As a particle approaches the speed of light, more and more energy is required to accelerate it further. The particle becomes increasingly resistant to acceleration. Early explanations of relativity often described this by saying that the particle's mass increases. Modern physics prefers to describe the phenomenon by saying that the particle's energy and momentum increase, while its rest mass remains unchanged. From Lorentz's perspective, the same effect can be interpreted as a consequence of motion altering the interactions that hold matter together, making further acceleration increasingly difficult. In Einstein's interpretation, however, no deeper mechanism is required. The effect simply follows from the relativistic structure of space and time. Whichever interpretation we choose, the observable result is the same. No material particle can be accelerated to the speed of light, because doing so would require an infinite amount of energy. Lorentz's interpretation is worth exploring because it provides a more intuitive way to understand special relativity. Einstein's theory can be difficult to grasp at first because it uses the same words as Newton: space, time, and length, while assigning them entirely different meanings. When we think about distance or time, we instinctively imagine Newton's absolute concepts. Einstein, however, speaks only about quantities that can actually be measured, using tools such as rulers and clocks. The difference may seem subtle, but its implications are profound. Lorentz's interpretation highlights the gap between our everyday intuition and physical reality. The idea of absolute time arises naturally from ordinary experience. At everyday speeds, all clocks tick at the same rate, chemical reactions proceed at the same pace, and we are inclined to believe that there is a single universal time shared by everyone. At high speeds, however, this is no longer true. Clocks run more slowly, radioactive decay proceeds more slowly, and even the aging process slows down. If these effects were easily observable in everyday life, we would probably never have developed the concept of absolute time in the first place. Lorentz assumed that these phenomena were caused by a deeper mechanism, an interaction between matter and the hypothetical ether. Einstein, by contrast, started from the assumption that the constancy of the speed of light and the principle of relativity are fundamental properties of nature. Rather than introducing unobservable mechanisms behind the scenes, He built his theory entirely on what experiments actually revealed. In practice, the two theories produce exactly the same measurable results. The difference between them is primarily philosophical. According to Lorentz, there exists a preferred background, the ether, but it cannot be detected. According to Einstein, no such assumption is necessary. Since no experiment has ever succeeded in detecting the ether, most physicists embraced Einstein's simpler and more elegant approach. This was not because Lorentz's calculations were wrong, but because Einstein was able to describe the same physics with fewer assumptions. This raises an interesting question. If relativity no longer needed the ether, what happened to it? Was it simply discarded? In a sense, yes, but not entirely. Like absolute space and absolute time, the ether faded into the background because it could never be detected. If something has no observable effects, physics will eventually abandon it. But then what, exactly, do light waves propagate through? Einstein's original answer was that no special medium is required. Light does not travel through some invisible substance, it travels through space itself. Space is no longer merely emptiness or a passive stage on which events unfold. It possesses physical properties of its own and is capable of carrying electromagnetic waves. The story, however, does not end there. When Einstein developed general relativity, space assumed an even more important role. In this theory, gravity is no longer treated as a conventional force. Mass and energy modify the geometry of space and time, and curved spacetime determines how objects move. Planets do not orbit the sun because some invisible force pulls them around it. Instead, the sun's mass curves spacetime, and the planets follow their natural paths through this curved geometry. Interestingly, Einstein himself later came to believe that spacetime was similar to an ether in a certain sense. In a lecture delivered in 1920, he explicitly referred to it as a gravitational ether. He did not mean that there exists a preferred frame of reference or an absolute state of rest. Rather, he meant that spacetime is not empty nothingness. It has physical properties. It can carry energy and momentum. It can curve, it can ripple, and it can influence the motion of matter. In this sense, the ether did not disappear completely, it transformed. The old mechanical ether vanished, but it was replaced by something far more sophisticated: dynamic spacetime. It is no longer a passive background, but an active participant in the physical world. The crucial difference is that, unlike Lorentz's ether, it cannot be used to measure absolute motion. For this reason, modern physics no longer uses the word ether, even though certain aspects of spacetime still resemble the original idea. One of the most important lessons of relativity is that physical concepts must ultimately be connected to observations and measurements. This principle becomes even more important in quantum mechanics, but it is already essential for understanding relativity. Abstract concepts such as Newton's absolute space and absolute time have no directly measurable physical meaning. In some situations, they can even be misleading. Scientific progress often requires us to abandon concepts that are disconnected from observable phenomena and replace them with descriptions that are more closely tied to experience. Physical time, in the end, is simply what clocks measure. It is not a universal background shared by everyone, but something that becomes meaningful through the physical processes occurring in nature. When we say that time passes more slowly aboard fast-moving spacecraft or near massive celestial bodies, it sounds mysterious and almost magical. Yet the same phenomenon can be described in a different way. Every process capable of measuring time, whether a mechanical clock, an atomic clock, radioactive decay, or even human aging, simply proceeds more slowly. This perspective is often closer to our everyday intuition, even though it is merely another way of describing the same physical reality. The relativity of space and time fundamentally challenged the classical idea of an absolute reality, and revealed that our picture of the world is only an approximation of the truth. At the same time, relativity is not necessarily as mysterious as it first appears. Lorentz's interpretation, in particular, shows that relativistic effects often emerge from familiar concepts, viewed in a very different way from how they were imagined in Newton's era. Relativity has shown us that space and time are not as absolute as our everyday experience might suggest. For many people, that realization alone is already surprising. But the story does not end there. If relativity taught us to rethink our understanding of space and time, quantum mechanics forces us to reconsider the very nature of reality itself. If you find these questions fascinating and would like to explore the most intriguing ideas surrounding relativity, quantum mechanics, consciousness, and the nature of reality in greater depth, you can download the book Simulated Reality, which inspired this video, completely free of charge. You'll find the link in the video description. And if you enjoyed this video, please consider giving it a like and subscribing to the channel. It may seem like a small gesture, but it helps these videos reach more people who are curious about science, physics, and the deeper questions of reality. I'd also love to hear your thoughts. Do you find Einstein's or Lorentz's interpretation more intuitive? Did this video change the way you think about space and time? Let me know in the comments below. Your feedback and discussion help shape future videos and make this channel a better place for everyone interested in these topics.